Hey there, fellow machine learning learners. Welcome back to our channel where we explore the exciting world of artificial intelligence. I'm your host, Bhaskar, and today we have a fascinating topic lined up for you. Are you ready to unlock the power of support vector missions? Well, get ready because we are able to delve into the world of SVM and discover how it can revolutionize your machine learning projects. But before we dive in, let me quickly introduce myself. I am machine learning enthusiast and educator and passionate about simplifying the complex concepts. In this video, our goal is to provide you with in-depth understanding of support vector missions and how they can be used for classification tasks. SVM is not just any algorithm. It's a popular and highly effective method for solving classification problems. So let's get started. When it comes to the classification task, support vector missions or SVM shine as one of the go-to algorithms. In fact, they have become a favorite tool for data scientists and machine learning practitioners. In this video, we will explore SVM from every angle and understand its significance in the field. Well, let's move on to section 1, understanding support vector missions. Our journey begins with the first session, understanding support vector missions. So, what exactly is SVM? Well, imagine a scenario where we have data points belonging to different classes and we want to find the best way to separate them. That's precisely what SVM aims to do. Find an optimum hyperplane that maximizes the margin or distance between decision boundary and nearest data points. To simplify things, let's consider linearly separable data where a straight line can perfectly divide the classes. This is where linear SVM comes into the play. It uses a straight line known as hyperpair to create that separation. Well, let's take an example. So we have a axis. These are our data points, and these are our data points. We will have a line to separate these two data points. So let's take this line as wx plus b. It is the equation of straight line which separates these data points from these data points. So this is linearly separable data because this data points are separable by a line. Okay, so this is equation of line. So it has two sides, this side and this side. So this side will be wx plus b greater than 0 and this side will be wxb less than 0, right? We have two classes and the line separate these two classes. If we go in one direction, wxb greater than 0. If we go in other direction, wxb less than 0. Can it be just one hyperplane? Can't we separate like this or like this or like this? What can we do? We can separate data points by different lines or different hyperplanes, but which hyperplane to consider? Well, we'll consider hyperplane which is having maximum margins. That means if these are the data points and these are our points, so try to create a line and these points and these points will be our support vectors. So support vectors are nothing but the points which are nearest to our hyperplane. So the distance between this point and this point will be our margin. So we will draw two lines, line 1 and line 2. Make sure that these two lines are having a equal distance. Okay. So we have two classes separated by a hyperplane and this will be our decision boundary. lines. Okay. Yes. We create two texture boundary lines and create a margin. Take the hyperplane having the maximum margin. We can't ignore the concept of support visual. These are the data points closest to the data boundary and play a vital role in the defining it. Okay, we have two hyperplanes w x1 plus b equal to 0, w x2 plus b equal to 0. So if we subtract them, w x1 minus x2 equal to 0. What does it mean? It means W is orthogonal with this vector. X1 minus x2 is a vector. So that means W and x1 minus x2 are perpendicular to each other. What is W? W is our weights. X1 minus x2 is nothing but a texture boundary to simplify it. That means if we have a points, if we have a line, this will be your W and this will be your texture boundary x1 minus x2. That means this line is perpendicular to this line. But what if the data points is linearly separable? Then we can use Kernel trick. It enables SVM to handle nonlinear data by projecting into higher dimensional feature space. This transformation allows us to find a hyperplane that separates the classes even in more complex scenarios. SVM algorithms use a set of machine learning functions that act as a kernel. Function of kernel is to take the data as input and transform it into the required form. Different SVM algorithms can use different types of kernel functions like linear kernel, nonlinear, polynomial, and sigmoid, etc. So the linear classifier relies on the dot product between the vectors. A kernel function is some function that corresponds to inner product in some expanded feature space. So in our equation, if we have any dot product, simply replace it with the kernel function. That's the kernel trick in simple terms. If there are two data points, d1 equal to p1 comma q1 and d2 equal to p2 comma q2. So these are two data points. I will just take in the matrix form p1 q1 p2 q2. So we want to take a square of d1 and d2. We have two options. Either multiply d1 and d2 and take the square, or take the square of d1 separately, d2 separately, and multiply them. So which is better? This will be better than this one, right? That means, so if you multiply this one with this one, we will get p1 q1 plus p2 q2 and take the square. This is the color trick. So what does it mean? It means in this case, multiplying and squaring is equal to squaring and multiplying. So we can, this is just for square. We can do it for higher dimensions also. Examples of kernels. They can be linear kernel, which is xi and xa. That means we're just simply leaving dot product as it is. They can be sigmoid kernel, like tan h of beta naught xi plus xi xj plus beta 1. There can be Gaussian kernel e power minus of xi minus xj whole square by 2 sigma square. They can be polynomial kernel like 1 plus xi xj whole power p. This is polynomial kernel. Like this, there can be any number of kernels. Even we ourselves can define a kernel if it follows certain rules. So, how will you use a kernel? As I said, We simply replace the dot product Si and Xj in the equation with the corresponding kernel. That's all. Now let's look at how we can train our SVM model. We use a loss function which is hinge loss. What is hinge loss? 1 minus Wx plus b into y. This is our hinge loss. We are already aware that we use a hyperplane. Hyperplane in this our example is Wx plus b. So it is equal to 0 the equation of a line. It can be greater than 0 or less than 0. So y can be greater than 1 or less than 1. So if you multiply Wx plus b into y, this entire equation can be greater than 1 or less than 1. We are only taking the sign. That means if 1 minus Wx plus b into y, we are just taking the sign. It can be greater than 0 or less than 0. If it is greater than 0, then it will be classified to a one class. If it's less than 0, then we will classify into other class. Combined with the optimization techniques such as gradient distance, such as gradient descent or quadratic programming to find the optimum hyperplane. It's fascinating to see how SVM takes advantage of mathematical principles to make accurate predictions. Now that we understand the inner workings of SVM, let's move on to the advantages it offers. SVM has the remarkable ability to handle high dimensional data with ease. It doesn't get overwhelmed by vast amounts of features, making it a reliable choice for complex problems. Additionally, SVM is resistant to overfitting, which ensures robust generalization to new data. So it means it is resistant to overfitting and robust, and we can use it for high dimensional data. With the foundations laid, let's move on to our next section, SVM in classification task. This is where things get even more interesting. SVM is primarily used for binary classification tasks, where it learns to classify instances into two classes based upon chosen hyperplane, just like previously how we have defined it. The decision boundary is the key here. SVM aims to create a boundary that separates the classes with a maximum margin. By doing so, it minimizes the risk of misclassification and maximizes the model accuracy. So, we are defining a hyperplane with maximum margin that minimizes the risk of misclassification and increases the model accuracy. Now, let's explore some real-world examples where SVM can be applied. Imagine using SVM for spam detection, where it learns to distinguish between legitimate emails and spam messages. Or consider the field of medical diagnostics, where SVM can aid in cancer diagnosis by classifying patient samples. It's important to choose the right kernel function based on the characteristics of our data, whether it's linear, polynomial, Gaussian, or whatever kernel it is. Understanding your data and its underlying structure will help you to make the informed decisions. By analyzing the support vectors, SVM gains insights into classification problems at hand. But what if our data isn't perfectly separable? That's where soft margin comes into the play. Soft margin SVM allows for a trade-off between maximizing the margin and allowing some misclassification. That means we have a line and we have two decision boundaries. As I said, if the points should be above this points or it should be this direction. If there are points here, that means we are having misclassification. The points are misclassified. These points are. So this will be our margin. We have to make assumption such a way that we have maximum margin and misclassification should be minimum, and that's our hard margin. What is soft margin? So soft margin will allow few points to misclassified. That's our soft margin. So we have to find a trade-off between maximizing the margin and allowing some misclassification. Or what is our objective function? Well, we can define it as half into W into W, the weights, plus some C into some slack variable. This is our objective function where C is hyperparameter, and if C is large, then margin will be small, and if C is small, margin will be high. So let's take an example. If C is large, margin is small. C large. If C is small, margin will be high. Margin and C is small. Okay, fantastic. Now that we explored SVM in classification task, it's time to dive into our finance section, practical tips and applications of SVM. In this section, we'll discuss some practical tips to help you use SVM effectively and explore its diverse applications. When working with SVM, it's crucial to pay attention to practical aspects. For example, feature scaling ensures that all features contribute equally to model's decision-making process. Moreover, when dealing with imbalanced dataset, techniques like resampling or using class weights can help improve SVM's performance. In resampling, we are simply resampling the sample data from population. That's what we are doing in resampling. SVM isn't limited to binary classification. We can use it for multiple class classification by using techniques like one versus one and one versus resh. We have already discussed these techniques in the previous sessions. So please go and watch previous video to know more about these techniques. Now let's talk about exciting real-world applications of SVM. It's remarkable to see how SVM has made significant contributions in various domains, from image recognition to text classification, bioinformatics to financial market analysis. SVM has proved its mettle time and time again. Like any other algorithm, SVM has its strengths and limitations. SVM offers great flexibility. It's important to understand that its performance is highly sensitive to the choice of hyperparameters. Additionally, SVM can be computationally complex for very large dataset. Before we wrap up, let's touch upon some recent advancements and extensions of SVM. Support vector regression and support vector clustering, all exciting areas where SVM can be further developed. SVR, support vector regression, takes a different approach by using support vectors to define a flexible and robust regression model. In simple terms, SVR works by creating a line or hyperplane in high-dimensional space that best fits the given data points. The goal is to find a line that maximizes the margin, which is the distance between lies and closest point. So, what exactly is SVR? Let's take an example. We have our data points, that is our line. These are our boundary points. So, we to create SVR, we make sure we have some misclassification points. These are our misclassification points, and we fit a line all these misclassified points. That's our regression line. That's our SVR line, right? And we also have to make sure we have optimized margin. That is what SVR is in simple terms. This tube is like a tube. This tube is called epsilon tube. It's the region around the line within which errors are tolerated. Data points outside the tube contribute to the error and not penalize. To make predictions using SVR, the algorithm finds the best fitting line or hyperplane that minimizes the error while still staying within the epsilon tube. Support vector missions have certain assumptions. Let's go through them one by one. Assumption number one, linearly separable. The basic assumption of SVM is that data points are linearly separable. This means that there exists a hyperplane that can perfectly separate the instances belonging to different classes. If data is non-linearly separable, then SVM employs a kernel trick to transform data into high-dimensional space where they can be linearly separable. So let's understand a little bit about this kernel trick more. So if you have data points like this and you can't separate them, what will you do? You convert 2D into 3D, and in 3D we can separate them simply by a hyperplane. It will be a plane. So for 2D line and for 3D, it's a plane. As the dimension increases, dimensions of a hyperplane also increases. Assumption number two, feature independence. It assumes that features are independent of each other. The algorithm works best when features are not strongly correlated. Assumption number three, feature scaling. SVM assumes that features are scaled properly. What if features are not scaled? Then there will be a bias. So, what can be the solution? We can normalize or standardize the features so that they are having similar scales. Next assumption, outliers. SVM is sensitive to outliers, especially in cases where margin is small. Outliers can significantly affect the placement of decision boundary and support vectors. So let's assume these are our data points and these are our major data points. Ideally, this should be our hyperplane. If there is a data point here, so then our hyperplane will be changed if it's a hard margin. Then our hyperplane from change from this will be changed from here to something like this. That means this will be our new hyperplane. Next assumption, data representation. SVM assumes that data is represented in a vector form where each instance is described by a fixed number of numerical and categorical features. Text or image data, for example, needs to be converted into numerical feature vectors before being used with SVM. So this point we will be using for when we are doing coding. So we should have fixed number of features. How the machine learning algorithms work, they should have fixed number of features. Maybe it categorical or numerical, it doesn't matter. They should have fixed number of features. It's important to note that while these assumptions can provide guidance when working with SVM, the algorithm is also known for its flexibility and ability to handle various types of data. In practice, it is advisable to assess the data and experiment with different approaches to determine the suitability of SVM for specific problems. We have covered a lot of ground today, exploring the ins and outs of SVM. We hope you have now solid foundation and understanding of SVM and its application. But remember, learning doesn't stop here. We encourage you to explore SVM further and experiment with it in your own machine learning projects. Don't hesitate to tweak hyperparameters, try different color functions, and embrace the power of SVM in your quest for accurate predictions. If you are hungry for more advanced algorithms and techniques, Be sure to check out our other videos in our machine learning mastery playlist. We have a treasure trove of knowledge waiting for you. Before we part our ways, we have a small request for you. If you find this video helpful and enjoyable, please hit that like, subscribe, and share this video with fellow learners. If your support means the world to us and keeps us motivated to create more valuable content. Thank you so much for joining us today. We appreciate your time, enthusiasm, and dedication to mastering the machine learning. Remember, the journey of learning is an exciting one, and we are here to support you every step of the way. Keep exploring, keep experimenting, and until the next time, happy learning. Thank you.